just labeled my binders.
Then just
Third week of class, I labeled my binders today.
I don't even have a binder.
Well, then, will you have one by the fourth week?
I won't have one by any week.
We need a 3-hole. Oh, there is a 3-hole punch.
You could just go down to Amy and do it.
We have to harass them constantly.
Well, you go into the copy room and there's one in there.
I have a tendency to harass people. I have to stop and harass.
Just go in the door by Greg's
Walk in.
office.
Keep walking.
No, go down the stairs, through the secret door, and back out the secret door and up.
I always like to ask them, like, use it.
Oh, no, she doesn't care. I'd never ask you. No, it's not. If it's the offices, it would be more rude to interrupt her while she's working. Like, it's not hers, it's the office. I'm sure
I think
Svetlana,
it's more rude to just use it and ask. So,
I'm sure Svetlana does not ask every time she goes and makes a copy. Can I use a copy?
that's what that group is for.
Yeah, that's what those 3-hole punches for.
It's not for us.
It's for faculty. They have a password, yeah.
No, that's what faculty prep room.
Every
I've already-
faculty have a different password.
But you
So
don't
that's why I asked.
have a password for a 3-hole punch. You just 3-hole punch. Easy.
I asked if I can use a faculty.
In and out.
You have to ask if you use a faculty.
Oh, you have to have punch or printing.
Punch.
Punch will be big, yeah. It's not cost money, right? That's cost money.
No, you don't. That's ridiculous.
It's not your room.
No, you have to ask if you want to have a conversation.
Yeah. He knows what you're doing. You have to ask if you want to conversate a little bit.
I was in the conversation.
Yeah, so you don't ask and therefore you don't get in a conversation. I'm tired.
Avaya, please enter your...
Oh, thank you.
The conference is now starting. You are the first person to arrive. You will now be placed into the conference.
Thank you.
The conference with us. I feel like we should go into separate rooms just to utilize the technology.
Oh, if everyone will sit in a separate audio isolated room with a separate mic, this would enable. Aaron saw it on the group meetings, right? Last time when you were in a different state.
Mm-hmm.
So whoever speaks louder will pop up to the central screen with and you can share whatever is on your computer. Like if you are doing presentation, everyone sees it.
That might be bad if I'm in that conversation.
Oh,
You're loud?
Yeah, you make fun of me all the time about it.
I know. Well, like, inside voices.
This
Says,
is
no,
my
I'm not
voice.
loud.
So we are missing Sam.
Yeah, I wonder if the bus is just always late.
What class do you have at 1, Aaron?
Nanotech?
Nanotech?
Yeah, that's just across the road.
What road? That road or that road?
Which way's north?
That road.
Yes,
That way. Yeah.
Dolby.
Oh, so it's in the engineering building?
Yeah, the mechanical.
Physics buildings and
Wait, is it Kalpana Katti class?
South.
No, which
No,
class?
that's south.
Is it Kalpana Katti class?
South
Who is the
engineering.
instructor?
That's the
Patty.
physics building.
Yeah, Katti. Kalpana Katti. How is that going on?
Not too bad so far.
No,
I mean,
Do you give
Man,
your
she can,
mix out again?
she can talk a horse's ear off.
she's
That's
just talking and
She's full of knowledge, but
Okay,
she just goes down the roads.
no.
Beef.
Sam
It'll go
seems
from
to
the
be
class.
too busy for the class.
Aw, sad day.
Did he email you?
What?
Did he email that? They used to-
Yes, yes.
Okay.
Then it will be democracy for you and a strict assignment for you. So, welcome to the meeting number 6 of the quantum chemistry, second chemistry 767. We are completing the chapter on angular momenta and moving on to the perturbation theory. Our today's meeting will be split between angular momentum and beginning of the perturbations theory, and coming Tuesday you will volunteer to make presentations, right? So please mark your first and second choice on this piece of paper. Only one copy, so that it circulates, comes to me, and if there are no conflicts, then it will be according to your wishes. If there will be conflicts, I will try my best to resolve them. Levi has his own opinion about this procedure and
No, that
whether
was Brendan.
Brendan, whether it can be called democracy.
That was Brendan.
What?
That's okay.
Okay, regulated democracy.
No, we're actually a republic.
No, I am telling about the way
This.
of selecting subjects for presentations.
You're an electoral college.
Okay, you can try to make this analogy.
Terrible.
We give him a vote. He just has.
Oh.
Okay.
So, what are we doing?
Socialism.
No. Oh, this one. So what are we doing today? We are quickly recalling what we did last time, and we will be bring it to the right place. So there will be 4. Well, originally the plan is for 6 chapters, but at least 4 will be done. We are coming to the end of the first chapter, and next Tuesday there will be presentations that do not do them long. We are limited in time, and the nature of this course that not everything is straightforward logic. Some of the pieces are miscellaneous pieces of knowledge, but they all are connected to practical examples, to real life. So try to make an example how what you've heard in the couple of weeks in the class connects to what you are interested in the research. So, as a little okay, as I'm speaking, you are feeling the list of subjects, which the easiest subject will be covered right here, if you are selecting for it. And you can just expand a little bit. We do not have anyone in this room starting at 11, and since some of us have other classes at 1, I suggest we will be conservative, not radical. We'll just start maybe at noon. Starting from the time of your presentations, next Tuesday. Objections? No, thank you. Then it would be great if we accompany this course with like office hours, questions, answers, free will labs, and you are invited to visit QBB 132. Originally, I was planning meeting from 5 to 7, but I know that some of you need to contribute to the teaching process from 5 to 6. So I wonder, would you feel more comfortable if you start at 6 and do as long as it is needed?
Which I can be.
You can give your feedback to me in private.
Yeah, that's fine.
Okay, who teaches at 5 to 6?
The for
The gentleman in red.
Oh, I see.
Yeah, that's fair. Okay, so what we did last time, we did completed the rigorous theoretical derivations related to angular momentum. Now we are doing more of the notations and intuitive addition of angular momentum for practical applications. If needed, we can apply our knowledge about Clebsch-Gordon coefficients, and there is a way to develop further in the theory of addition of angular momentum towards precise calculation of selection rules, precise calculation of transition dipoles and oscillator strengths for systems with high angular momentum. But we are limited in time, and we will stop just by giving correct naming for high angular momentum states. So what, please remind me when we go from one chapter to another one to make a little entertainment. I have prepared it, but I may forget. So just raise hands and entertain us. So if we consider heavy metal that has many elements, each of which contribute angular momentum associated with orbital motion and angular momentum associated with spin, then one can discriminate configurations of such ions that are different by specific values of total angular momentum that comes out from different summation, different addition of this angular momentum. And so-called Hans rules help to identify the state that is lowest in energy, from which of the state is different with specific angular momentum has the lowest energy. For spectroscopy of heavy metals, one often needs to name these terms of multi-electronic states, and there is a convention that we went over last time, Russel-Sounders terms. So if we are speaking only about ground state, and in most texts one identifies only ground state of a selected ion, Russel-Sounders term. But if you go to spectroscopy, one needs to be able to name excited states. Also, if we are doing boring hydrocarbon organics and we do not have radicals, then most of the compounds are closed shell. Number of up and down electrons are equal, and there is nothing interesting related to angular momentum. But as soon as we go to open shell metals, it is more interesting. And in order to name and identify different excited states, one needs these notations. Also, for heavier elements, the spin stops being a good quantum number. And the typical selection rules of spin conservation upon photoexcitation are lifted. So there is an ability for spin flip excitations. So we are going to quickly try naming some ground state, excited state with typical selection rules, and excited state that violates selection rules. Because if you go to heavier elements, they all are needed. So what are those? What is S?
S.
The sum of the spins.
Yeah, total spin of all electrons. What is L? total addition of angular momentum of all electrons in the ion. And what is J?
L.
Just adding these two together in a vector in the right way, right? So I am going to make an example of a couple of lanthanide ions. If you are, did you make your, everyone made choices? So most of colleagues didn't select transition metals, which means that as they understand how dangerous transition metals can be. Only two of you are brave enough to do that. If you go to transition metals, the situation becomes even more complicated because the d orbitals are protruding out of the core and they interact with neighboring ligands. And then there is a so-called ligand field theory or crystal field theory that makes offset of the orbitals with different values of angular momentum. What we are doing right now is more applicable to in case of absence of the splitting. If there is a splitting, the terms are a little different and one needs to make an extra effort to explain what it is. But lanthanide ions, they are heavier and there are some interesting effects because there are challenges, but there is no challenge associated with crystal field splitting. So they are good examples for the notation. So all states with the same orbital quantum number, but different orbital projections are nearly degenerate, at least for the purpose of notation. So there is no drastic change as in crystal field splitting. So if we take this. Also in nature, in chemical compounds, all of the lanthanides take 3+ oxidation state. And if you look on the periodic table, then looking from left to the right, they will have configurations 4F1, 4F2, 4F3, 4F4, and so forth until 40. So serum, 3+, 2, 3+, medium, 3+, and so forth. I'm just lazy and tired to continue. But we all should have periodic tables on the wall or at least in our computer. If you, well, I doubt, but if you never saw periodic table, you can type in your Google window ptable.com, and it is a very entertaining, interactive table. When you just bring your mouse marker towards element, it brings up information. It can show orbitals and show the occupation, like the Au principle. You'll enjoy it. The looking on this site is worth of like several lectures and maybe a few books. So last time we agreed that one can compute total number of microstates, make a table of microstates, and then intuitively deduce what will be addition of what will be the value of total angular, total spin, and total J. For some simple examples, one can skip it. This table of microstates is definitely needed for complicated examples. If you have a couple of electrons, we can skip it and just do the one microstate associated with field according to Hund's rules. M equals 3. M L equals 3. M L equals 2. M L equals 1. and L equals 0, and L equals minus 1, and L equals minus 2, and L equals minus 3. So we are considering only 4F shell because it is the only incomplete shell. Others, those shells that are fully complete, do not contribute to angular momentum. So we have only one F electron, and according to Hans' rules, it will populate in here.
What element are we doing, sir?
Cerium.
All we're doing is Syrian?
Cerium.
I never heard of that. Okay.
Oh,
It's right
the
after the line.
serial.
When I was a kid, at the city when I was growing, there was like several plants.
Oh, Zeri.
Right. Yes. So and from the like some kids were playing with waste from the plant, and the waste of the serum, they're just little pieces, like heavy metal of the very pale gray, and if you touch stone or other metal, it makes sparks.
Oh, that's cool.
So you can just drop a little of gas on it, throw, and it will start flaming. Or there were some more dangerous games.
I can only imagine.
Okay, so 1 ampere electron from, well, there is no reason to make microstates. We can see that spin can be +1/2 or -1/2, right? Up or down. So that S, that's we are doing ground state of cerium-3+. So we see that total spin is 1/2, and total angular momentum will be 3, right? We have 3, that's it. If we would have more electrons, we would add this index from each cell that is populated. So L equals 3, and for spectroscopic notation, they use alphabetic table. Uppercase letter S, P, D, F, G, H for 0, 1, 2, 3, 4, 5. So we have L equals 3, which should be encoded as letter F. Okay? And then for J, if needed, we can apply our deep knowledge about Clebsch-Gordon, but now we are doing just intuitively vector addition. So it is either 3 + 1/2 or 3 - 1/2, which could be either 7/2 or 5/2. So based on third Hans rule, one selects the state with minimal total angular momentum. So although both of them are possible, this one will have minimal energy. So this all will result in, so S equals 1/2, so 2S + 1 will be equal how much? How many? 2.
Which of the Hans rules was that?
Third.
Third. Okay.
The handout with larger font that I distributed last time, it doesn't have doesn't have title Hans rules, but it lists all three rules. So it would be double F 5/2. Okay, so it's ground zero. Now let's go to the table. And cerium-3 plus colorless electronic configuration xenon 4F1 spectroscopic term 2f5 halves. Okay? So we are able to reproduce it. What does happen if we excite it? There are two pathways for excitation. Well, there are many possible excitations, but there are two pathways. One is to excitations. Camera number, setup number 5. Okay, good. So, so this electron can be moved to electronic state with different value of orbital momentum. So delta S equals 0, delta L equals plus minus 1. So it will be standard, what we can do. And in addition, there is a transition that is forbidden in regular spectroscopy with spin flip. When we keep, for example, we can keep it in the same value of angular momentum but change the value of the spin, flip the spin. Or if everything is skewed, you can jump to another cell and flip the spin. But those are possible. And one should take into account such states when doing analysis of excited state for these heavy ions with non-zero angular momentum. So if we are looking for delta L equals plus 1, serum excitation of serum 3 plus. So it will be spin up, but in the different cell. So the spin is still 1/2. Now the total angular momentum will be equal to 2. Yes, because it is in the quantum state with correspond to the quantum number 2. 2. And in the spectroscopic notations, 2 will be D capital, right? Now for the J, it will be 2 plus minus 1/2. So it will be either 5 halves or 3 halves. And for the, due to Hans rule, we select the lowest spin. So S equals 1/2, which means 2S plus 1 will be 2. So it is again doubled. D capital 3 halves. So it's one of the excited state of the serum ion without flipping the spin. Now the spin flip excitation. Spin flip excitation. So if we stay for F, so we stay in the same cell, but we flip the spin. Spin, flip, serum 3 plus. Well, total spin is still 1/2. The L equals 3, which corresponds to F symbol. And because we are changing the spin, it will be different result of this addition of angular momentum. So J will be 7 halves. Doubled F 7, which will be higher in energy than the ground state. So if we find out a research paper on spectroscopy of lantanides, they will have spectra where each line is labeled with transitions like F to 5 halves to doublet F sub. Symbols like this.
How do you know that energy is flowing?
There is a way to compute it, and there is a way to find it experimentally. But then the name of the course will be not quantum 2, but heavy physics of physics of heavy ions.
A question.
Yes.
Why is J7 halves? Because Hans rule is for ground state, right?
And it is not a ground state.
It's
anymore.
not ground
It is an
state,
excitation.
it's
Oh, so you're choosing the others, yeah, just the other option.
Should we try another one? Or if you, let's probably do it.
Isn't he gonna do them all?
No, there is still plenty. We spent like 20 minutes for one of them, and there are 40 continents. If
Oh, I guess if we had 2 electrons, that would make it.
okay, let's do 2 electrons. So what's the name for the one with 2? So it is PR. For the praseodymium. And let's move it around.
What is
First, praseodymium. So if you look into periodic table, it has the main block and then it has 2 blocks underneath. One for lanthanides, another for actinides. If you look onto lanthanides, then this one will be the third in this line.
I have a question about the actually previous one, spin flame one.
Uh-huh.
Why s equal to plus half?
Because it is total spin, it is not projection. You can have 1/2 and minus 1/2, but it's still total spin is 1/2.
1/2.
So it's the magnitude of spin?
Yes,
Oh,
it's still a doublet.
thank you.
So first time I've heard about Hans' rule was in the
second grade?
huh? No, not second, but maybe
You guys
fir-
learned it.
first year of high school, and explanation was very brief. Like, if you need to go to use public transport, bless you.
Thank you. Yeah, this is.
And you are the only one. You take any seat, and usually in public transport they are just 2 love seats everywhere. If you are the second person, you will not sit near the stranger. You'll find the next seat, and then the next one will find the next seat. And when all seats are populated half, then the next person is induced to sit nearby someone else. So therefore, for praseodymium, it will be up and up in the next cell. So the spin will be 1/2 plus 1/2, 1, right? Which means that 2s plus 1 will be equal, how many? 3. So it will be triplet. So 2 spins with the same projection. Well, not always the same, 2 spins that have opportunity to have the same projection. There are 3 microstates when both up, both down, or opposite. It is a triplet. Now, for total angular momentum. 3 from first electron, 2 from second electron. 3 plus 2 equals how many? 5. Let's practice alphabet. S, P, D, F, G, H, I. I'm not good at alphabet. And letter E is skip. 0, 1, 2, 3, 4, 5. So number 5 will correspond to symbol H if I didn't make mistake with alphabet. for the J, we take 5 plus minus 1, which can be either 7 or 4. 6 or 4. Yes, thank you. I appreciate your mathematical help. And because of the third Hans rule, we select 4. So the minimal value of the total angular momentum. So this all will consolidate into triplet H4. Let's check with the table. Praseodymium, green, xenon, 4F2, triplet H4. Okay? I can recall the alphabet. So what would happen if we do excitation with delta S equals 0, regular excitation of praseodymium 3+, that is allowed by selection rules. So we can move electron to one cell up. And there are several available excitations. We are showing just one of them. Starting from next week, probably it's last time we need to leave earlier, because we will shift the beginning to earlier time. And we are shifting to the noon, but we can shift much earlier if there will be vox populi, voice of people. Okay.
And 9.
So we're removing one here and placing it there. Then the spin is still 1. 2s plus 1 equals triplet. The L would be 3 plus 1 equal 4. So which means we drop down one letter, which will be G single. And the J will be 4 plus minus 1, either 5 or 3, and we select 3 because of Hans rule. So which will consolidate to triplet G3. And for delta X spin flip excitation, of praseodymium 3+, we are flipping the spin and trying to follow the Hans rules as much as possible. Well, this table doesn't allow to check whether this was correct. Typically, tables show just ground states. Otherwise, they will take 1,000 pages. So we take this spin, flip it, and move it to the cell to maximize the total angular momentum according to the second Hans rule. So it will be up and down. This with the rest staying empty. So spin will be 0 with 2s plus 1 equals 1 single. The L will be equal how many? If they both are in the angular momentum projection suite. So 3 plus 3 equals 6. And in this alphabetic, it will be I single, right? And for J, it will be 6 plus minus 0 will be 6. So putting all together, single I 6. So like lowest spin flip excitation for praseodymium will be 3H4 to triplet H4 to singlet I6. And but at least if you do the next one, neodymium, there would be very good reference in literature because neodymium is used for popular lasers, and there is a lot of literature on them to check about the excited states.
So if you do a spin flipped excitation,
Uh-huh.
you always condense it to
Yes.
3, even if you have like the half shell full, and you flip -3, that goes to 3, right?
We are looking for lowest energy
Oh,
excitation of this class.
okay.
What I'm not focusing in much details is that all of these terms are, most of these terms are degenerate. And they have several sublevels that have the same like if it is a triplet, it has at least 3 degenerates. And it also makes some influence on this factor. Now, I hope you do not have questions. I will have, it will be my time to ask questions about angular momentum when you make the presentation. Anyone needs to go urgently? Then let me erase all this stuff and start. Oh, I've promised you entertainment.
Yes.
Yes.
Everyone else lost it. So, Sam and Aaron are missing the entertainment.
It's not going to be recorded?
No, we can record the entertainment. What's wrong with this?
I'm excited for anything.
Oh. The second that you thought that you lost your control. Oh.
So,
So this is why you were asking about it.
yes. No.
I think I'm gonna back up.
No. It is not dangerous. So there are 2 propellers moving clockwise and 2 counterclockwise. If they're moving with the same spin, it is like a closed shell configuration with total angular momentum 0, right? But if we either block one of those or make those that are clockwise if the clockwise rotate quicker than counterclockwise, it accumulates total angular momentum. So it is an example of total angular momentum addition. And we can rotate it in another. So if you disbalance the angular momentum clockwise and counterclockwise. Or we can like put something to block one of the motors, and then it will be like spin 1/2. So you can play a little bit while I'm erasing it.
That's you, Brandon.
Starting the
Well, to me then, like,
So I think the left one is your power, the right one's the spin.
Oh, I picked that one.
because bring it up
Brandon.
like a pilot.
Oh, no, stop it. Stop. You're gonna, okay.
How do you stop it?
You just,
Here, you do it.
I've never used this.
Would you want to do it?
Hurt someone or myself.
Wait, what?
I'm confident graded courses should be fun.
You almost hit the bed in the face.
Put it back on the table.
Suddenly it's come to
You weren't gonna take a drone to the face to save your bed either. You just dodged.
Watch out.
Can you fly it?
You suddenly
Not much better than
Not
this.
better than that.
Oh, that's hilarious.
he can take off, but he can.
I pretty much just know how to go towards jump at. Good thing I got my safety glasses on.
So this is the power.
I don't know what the power is. I think one of
So
the.
what is the con?
I think
This is
one
the
of these
direction,
are
I
the.
guess. These are direction, I guess.
I don't know.
Where did you
We need
get
to
this?
figure out actually controlling.
Where did you get it, eh?
I didn't do anything.
It was not a toy store. It was like store for clothes. And you know, when you come to the tower, to the counter, they have some unnecessary things like chocolates or.
Oh, wait.
Or drones.
Wait, there's hair.
Drones, yes.
How do we turn it off? Turn it off quick.
Yeah, I turn it off from here.
It's still blinking though.
That kind of switch, I guess. Oh, they have a camera too.
Yeah.
Okay, we can play when we come. Yeah, after when we come next time. Let me start the new subject. I do not have a robotic demonstration for perturbation theory yet. So, what I will continue to do. So, entertainment done, major part. And we did examples of Syrian and Brazilian. If you were in the quantum 1 class, you noticed that there is like 5 problems that can be solved exactly in quantum theory. Like infinite box, harmonic oscillator, hydrogen atom, rigid rotor, well, and what something is not.
Finite box.
Huh?
Finite box.
Okay.
That's the other one, right?
Anything else? Finite box? No, it's not.
Infinite potential, well.
Okay.
But you said infinite box, that's a free particle, right?
No. Infinitely high box.
Oh, yes.
Not the length, but height.
I think like free particle. But that
Oh,
one,
free particle. Okay, 6.
like infinitely wide box, free particle.
So, but for practical applications, we need to solve other problems. And the rest of quantum theory means designing and using approximate methods. There are at least 2 directions. One is variational method, which we covered in computational chemistry, and most of quantum chemistry is based on variational methods. And another is perturbational methods. When any problem, well not any, but many challenging problems can be formulated as known problem with problems with known solutions, with a very little perturbation, a little interaction, a little contribution to energy, to operators that govern behavior of the system, that modify the solution to a very small amount. For example, so where perturbation theory is needed and where it is, where does it work? So, if you do have neutral atoms that do not have chemical bond near each other, if you do just regular quantum theory, they will have the orbitals, and even if you do multi-electron problem, if they far enough,
the binding energy will be negligible. But if one takes into account the electrostatic polarization, there will be van der Waals forces which will contribute term for their interaction, very small perturbation. Or an example that is very simple and easy to imagine. When we consider diatomic molecules or anything that vibrates, we do normal mode analysis, which means we assume that the interatomic distance although it is something complicated, we approximate it as harmonic potential, right? Right?
What is that? Oh, where?
Potential
Okay.
energy is delta R squared with some coefficients, which is like, right? There in potential energy there are terms of the delta R third, delta R fourth order, but in most of the molecules for low amplitude of vibrations, those contributions are small. And one can contribute these terms in the energy as a little addition on the top of harmonic oscillator Hamiltonian. And as a result, one would see very little change of vibration frequency and lift of the selection rules. You know, if one rigorously makes all the derivations for harmonic oscillator, one gets that the quantum number of excitations can change by 1, right? From 0 to 1, from 1 to 2, from 2 to 3, but not from 0 to 2. Those are forbidden. If one adds those, they become available. And such calculations based on perturbation theory can be easily compared to infrared spectroscopy. So this is one of the examples. Another example is when you have an atom, hydrogen-like atom, where all electronic states or orbitals are known because of the original unperturbed interaction is just Coulomb attraction of the ion and interactions of electrons to each other. But if one places this atom into electric or magnetic field, one can consider them as perturbation. That also changes the energies of orbitals. So generally, the philosophy of the perturbation theory is one of everywhere in the quantum theory, one tries to formulate Hamiltonian operator. So the philosophy is that one considers this as the unperturbed and small perturbation. This would work only in case that for unperturbed Hamiltonian, one can easily find the solutions. So eigenvalues and eigenstates. Before we go further, we need to make a disclaimer. There will be several chapters in the course, and one chapter will be time-independent perturbation theory. And then there will be time-dependent perturbation theory. Basically, at this point, 5 minutes from the start, we are basing everything on the time-independent Schrödinger equation and corrections that make solution more precise. Only the goal is to find set exact set of eigenstates and set of eigenenergies. In the next chapter, we will be looking onto time-dependent aspects. And there the goal will be to look how the occupations of quantum states change in time. But it will be in like 3 weeks from now. Now we need to focus on this. So some of you were in the computational chemistry course. And you remember the corrupt philosophy of density functional theory. In a good sense, I'm admiring of it. But one of the ideas in density functional theory is that we can imagine an artificial world where electrons do not interact, right? And we have a true world where electrons repel each other. And then there is a limit transition. There is a continuous transition between these two worlds by placing a parameter, like lambda, in front of the electron interaction term that is equal 1 in real world and equals 0 in this imaginary universe. So same idea is behind the perturbation theory. We assume that there is a true world and there is a artificial auxiliary world. So in true world, Hamiltonian is equal H0. In the artificial world, Hamiltonian is equal H0 plus perturbation. For example, if we are speaking about anharmonic oscillators in the otherwise. In the true world, we have anharmonic terms. In the artificial world, we do not have them. But then we can consider that one can first find everything for artificial world, and then slowly move to true world. By telling that here we also have this H prime term, but it is multiplied by parameter lambda. And this parameter lambda is equal 0 in the artificial world, and it is equal to 1 in the true world. And if we are mathematically carefully making this transition, then this lambda slowly increasing. So we can ask ourselves a question: how does the solution of time-independent Schrödinger equation will react to slow, continuous addition to a term in a Hamiltonian?
Wouldn't it just add values to the oscillating elements?
It is very general, and we are looking for solution. Sometimes it may mix states. Sometimes it may contribute transitions that were not available. It may change the symmetry. But the response of solution to small increment of extra term. So another idea before we dive into equations, that if one cannot find exact answer, one can always try to represent answer, the solution, in form of series. So identify a small parameter and find the answer in terms of like power series or series of some other functions. Select some good basis functions and represent answer as series, base function times expansion coefficient. And make the series as many terms in the series so that next term in series is getting smaller and smaller and smaller, and by adding together everything converges. Hopefully with small enough number of terms. Series that can converge. And energy is also series that converge. So series should have either functions, or if it is power series, then small parameter. So which functions, or if it is power series, then which small parameter. This is question, and here is answer. So we will represent both wave functions and energies with help of power series in powers of this parameter lambda. Because if we are very close to zero, then it will definitely converge. If it is higher up, things may happen. But at least at the beginning, we can count on this. Powers of lambda. So phi sub n equals phi 0 times lambda in power 0 plus phi 1 times lambda in power 1 plus phi coefficient number 2 times lambda power 2. And scientists making research in the area of theory that is named field theory. One representative of this area is in the class. Often go to higher powers, but simple guys like us often are happy just to say. And same for the energy. So first collection, energy, second collection. So there is a hope. All the philosophy in this approach is that if one has infinite series and one adds all together, then it will converge. So that each next contribution is smaller than previous one, and some additional requirements from calculus for series to converge. But even if it doesn't satisfy, it is a way to start with. So for many problems, it is possible to try this perturbation theory. So when we will go to details, I think it is enough for today. Then we will try to derive expressions for these corrections in terms of the perturbation Hamiltonian. In case, that's it. Questions? Please.
Do you know what topics we're doing? Or do you have to deliberate before sending it out?
I think everyone got their first choice.
I assume that.
No.
So
Dan will make his first choice. For sure. Brandon,
My one is toughest.
unless you object, you will do your first choice.
Okay.
You chose that. You're for your second.
Yeah.
I mean, you chose that for your first.
Did you guys choose the same one or something?
I asked Jabed what he was doing, and I was gonna do 13, and then I didn't really have a second choice, but his second choice was 13, so therefore no one else overlapped. But we'll see what the electorate.
So you have only one choice.
Yeah, because I knew that I wasn't gonna overlap.
What was your second choice?
I didn't have one because I didn't need to.
Do not follow instructions.
Okay, then you guys, and you have like 24 hours to decide, but you do your first choices. Just be aware that it is more complicated. You are selecting heavy thing.
All the rest look even worse. So
Wait, what'd you select?
Well, if you believe so, I'm happy. I will be happy to listen to your presentation on this complicated
I
subject.
don't know. Okay, I'll maybe ask talk to you later.
13?
13.
So everything with transition metals needs
13 is
additional
toughest
reading.
one, 12 is second toughest, 11 is third one. It's kind of ascending order.
Right? So the basic idea is that for this,
Yeah, they split.
they split, and then you are doing this diagram populating only the lowest ones. And if you add or remove electron from this routine, like in ground state, whatever. This term is full populated, but if you do either excited or ionized, then you remove one electron here, and then you need to count for the different angular momentum, different spin.
You need to account for the difference in the octahedral splitting.
No. Let's consider that it will be always octahedral, but you are doing either ionization or excitation.
Yes, but wouldn't.
Neglect change in the coordination of fluids. Otherwise, it is a thesis subject rather than 5 minutes presentation.
What purity is neutral anyway, right?
Yeah. No.
No?
No. Because I think isn't it an
Pretty sure what purity is
and
neutral.
no, it's charged.
So,
Light
we
reading is a neutral, right?
Yeah, so it ends in the
Is it
six-member
an
ring,
and coordination
six-member
number?
ring.
No, but that would mean that the ruthenium has to be neutral.
No, ruthenium is 3+.
No, there's 2
Yeah,
plus.
So we are missing just one spot in our original plan. There, I just don't want to overload you, although it is it wouldn't take much time, but we'll better do it when everyone gathers together. So the next step would be to take this series and plug them into Schrödinger equation and just see what happens. Plan for next Thursday. Next Tuesday, you will present whatever you can. Next Thursday, I will present how to plug these two series into this equation. It's probably easier. No?
You want our PowerPoints by Monday or?
Yeah, Monday night. Yes. Thank you for reminding me.
Were you in competition?
I was in the cells.
So with this, the meeting number 6 is done. Thank you for stopping by, and meeting is dismissed. We are going off